And then obviously, right, the standard univariate, bivariate, multivariate analysis that you touch upon, right, in the data set. So the key point that I want you to understand here, right, in terms of the data set is this specific graph. We'll come to it during the model deployment, right? If you do a histogram of the wines, by and large, bulk of the wines are in category 5 and 6, right? Almost 3/4, right, of the data lies in this category. If you look at it, the quartile 1 and quartile 3, right, they are in essentially the 5 to 6 range. And if you look at mean, that again lies between 5 to 6, right? And if you look at except quality 7, rest pretty much the data set is sort of negligible, right? Rest of the data sets around, let's say, quality 3 and quality 9, which are the lower and upper bounds, they are negligible, right? Or doesn't exist. You can almost say that, right? This is very key component, by the way, to understand with regards to the wine quality, right? When we go into details on the ML model. These are the various profiles, right? It's mostly right skewed, as you see. Certain chemical parameters like the fixed and volatile acidity, chloride component, they have big outliers, right? You can see that there are a lot of outliers for these features. While if you look at alcohol or density, they are, the outliers are very less, right? So that's pretty streamlined if you look at it. But then a lot of the input variables have the outliers, especially on the upper bound. This is again a quality versus individual parameter Rech plot, right? And you can see that except alcohol, which is obviously having a good positive correlation, rest of it may be citric acid, you have some correlation. You see density is negatively correlated and so on, right? Yeah, this again is what we mentioned earlier, just comparing 3 categories of wines and how they are spread in terms of all the 11 input variables, right? This obviously, right, I mean, takes the cake when it comes to overall our understanding of the data set. The correlation map, I'm sure all of you did it during the EDA, right? There, obviously, whatever we saw in the earlier chart sort of gets blown up in this particular correlation or the heat map, right? So-called. Density is having an extreme, I would not say extreme, but then very high negative correlation with fixed acidity, for instance, or for that matter, alcohol again shows a positive correlation, right? One more metric, in case if you haven't dwelled upon in the EDA phase, is actually very useful. This is called cluster map. It shows 2 parameters, right? Whatever we saw, the heat map is pretty much a 2D table. This is, I would say, a 3-dimensional table, which has the high, in fact, I would say even 4-dimensional, but it's not exactly 4-dimensional. It categorizes and links the various variables, right? And it shows a hierarchy. For instance, you see pH, alcohol, and quality, right? I mean, they are very closely linked in some fashion, right? I mean, if you look at it from a practical standpoint, higher the alcohol content, the higher the pH, right? And then the acidity and pH are inversely related that way. And the free sulfur dioxide, if you look at it, there is a link, right, with the total sulfur dioxide, and same with the residual sugar, right? Because residual sugar gets formed once the wine is formed. And free sulfur dioxide at that point is essentially performing a protection function, right, in protecting the wine against the microbes. So yeah, this is a very useful map. Again, trying to align with some of the practical findings that you see in this space versus what we saw in the earlier maps, right? Again, I did several of these metrics and comparisons, but obviously it's very difficult and very complex relationship. Sometimes there is a collinearity between the independent variables. So it was very difficult to physically make out what are the trends. Again, tried one more segmentation on the premium and the average plus poor wines combined. Right? So again, found few trends, but couldn't really come to a conclusion as such. This is another useful map. This is called parallel coordinates. So I took a sample, right, which is I think around a sample of 50 amongst the 6,000 plus the quality table that we had, right? And in that sample, how does average, premium, and poor wines fare? Again, you get some broad strokes, but then you are still not sure, right? You know that there is a high correlation between the alcohol and quality, right? And likewise, residual sugar is low in premium wines, right? Or chlorides are again low in at least some of the premium wines, right? And some higher. So again, it's another representation, right? So based on that, I came up with a rank, which is essentially indicating the green indicating the positive correlation factors, red indicating negative correlation factors, right? And what could possibly needs to be tightly controlled to get a good quality wine and so on, right? But these are again guesstimates at best. So obvious analysis was that further debug needs to happen, right? Into these parameters and their various interdependencies. And we need to build a model, right? And see how efficiently we can compare quality versus changes in the input variables. So yeah, I mean, with that, this is sort of redundant. Let me skip that. Yeah. So with that, let's go to the ML model and what models were chosen and what are our conclusion, right, based on the testing with the linear and logistic. And there was no specific reason for linear and logistic except that these were the first two regression or classifier models that were dwelled upon in that order, right, in the last term. But there are obviously more models which could bring in more accuracy. So far, are there any broad questions on the inputs or output? Any question, right, before we dwell into the ML stuff?
No.
Sorry, am I audible?
Yeah, you are. EDA part is okay. At least I am struggling to start or pinpoint from the ML. So this would be good to know.
Okay, super. Yeah, again, the models that was used is the scikit-learn, right? So even if you don't have the material, the standard scikit that you get on any of the portals, right? Whether it is on the scikit.com website or in any of the popular machine learning blogs, that normally works, right? What you need to do is to tweak these parameters, right? And then suit your sort of needs. And then what works for you may not work for me may not work for you and vice versa, right? So yeah, standard inputs, right? I also sort of come up with the additional 1 or 2 slides in the light of some questions that came up. But broadly, you do the data messaging or data preparation, right? With a bunch of the fit transform or fit or transform. And sometimes you choose not to pick all the input variables. You drop few of them and see how it impacts the output. So I think a lot of this is trial and error, and obviously based on the various scores, what they tell us, right? So those are used at multiple stages. And then second stage being the selection of the model. And I think around 4 or 5 different algorithms are available under the logistic regression model, right, in the scikit-learn. So you could try with any of this. There is a default one. I finally ended up using the default one. And the different algorithms work for different kind of data sets and different size of data sets. That's one thing which I understood when I was doing these trials. And obviously the last being the model evaluation, right? Yeah, so one of the things that we do, right, I mean, as we look into the data set, and mine again had around 6,000 plus observations, was to split it, right? I looked at multiple ratios of test to training. I found that from 30% onwards, right, or 35% to 25% or 20%, I was getting similar accuracy, similar other parameter scores, the true positivity rate and FPR and so on. So I the final one was actually, I think around 28% was what I used, but the results did not hardly vary, right? From a test size of 0.35 to 0.2, 0.25, at least for me, right? In the final algorithm that I chose. Then a lot of these are default, by the way, you may not even know. If you just give, the logistic regression without giving any of this, you will get a dummy result. And that should also be fine. I tried with liblinear and a couple of algorithms. The solver, right? The solver that we use could make a big difference in the accuracy and other metrics I mentioned. And that can also vary depending on whether it is binary classification or multinomial, right? So the one that I chose again was liblinear. That is one of the 5 or 6 solver techniques which are available as a part of Scikit logistic regression, right? And all these pretty much are the standard parameters. The intercept scaling was again default set to 1, etc. Right? So tolerance again, I tried changing some of these variables. The biggest difference that I found was on the solver itself, right? Rest of it did not make much of a difference in my data set. Even random state is something that you can choose to give a higher value, or lower value, but then that also, doesn't impact the accuracy. With that, again, the first one which I dabbled was linear regression. It basically assumes that there is a linear regression, right, between
I have one question,
IV.
Kiran. I have one question. What does random state do?
So I think it is a random the state, right, that
Yes.
the ML model will initialize and go from there. It's a heuristic that is used inside the algorithm, right? But that random value could be 300 or 100, right? What I find is it's like the symbol analogy, right? Again, I'm not an expert, but then to the extent I understand, it's like some counter at which the algorithm starts, right? But that doesn't impact the accuracy. So maybe I think if you're crunching some 1 million plus observations or something, these parameters would make a difference, right? So for our kind of data sets, thousands of data, hundreds of data, random state doesn't really matter.
Thank you.
Again, these are the textbook definitions, so I will not dwell much, except that linear regression works well when obviously there is a linear dependency, right, on the IV and OV, which wasn't the case in the wine data set. These are standard metrics, RMSE being the root mean square, right, error, and the adjusted R square being the coefficient of determination. And that R square is nothing but 1 minus the fractional variance, right? So basically, the mean error or absolute error are not typically used in regression models, while they are very simple to understand. So these are the ones that are typically used in linear and logistical regression. But from a theory as such, Jagat and Suraj, right, we did cover the absolute error, which is the predictor variable minus the absolute output, right? But those are not being used. These are supposedly more accurate for larger data sets and for regression. I also added, 2 categories, right? One is the country category and the wine taster rating, right? Which is the average, poor, premium. So I was in fact trying to bias the model, if you look at it, by giving that synthesized information on whether the wine is average or poor, right? I gave a variable which had that classification, and then trying to see, with that help, would the linear regression model actually predict the quality of wine accurately, right? As in to the T. But even that didn't help, right? So the other one was by randomly classifying the wines into the countries that are majorly involved in the wine making, right? Italy, France, US, Spain, etc. I created another attribute and saw whether this makes a difference. But between wine category and country feature, it did not make much of a difference. But obviously, adding a feature is improving the overall quality because the error is reducing, right? So that's the general observation. And this is basically my, then this spectrum doesn't change amongst the 3 trials that I did. The output variable and predicted variable, right? There was fair bit of miscorrelation. And the last one is the y equal to mx plus c, right? Equivalent equation for this set of input variables that you see. I mean, obviously, the association with your alcohol or sulfates or free sulfur dioxide is positive. And then that sort of adds up to our the older correlation map where we saw positive attributes there, right? And that translates into higher values here as well. And whatever was not correlating well, some of them, not all of them, by the way, residual sugar had a negative correlation there. But some of the other metrics are actually showing the right correlation, right? Like density or total sulfur dioxide, there is a negative correlation. Next, we move on to the logistic regression. So any comments, questions on the linear regression? By the way, the experiment was a failure, but it is done more for completeness and to see how does it fare, right? But obviously the model did not do a good job in predicting the right values.
So how much was the percentage of testing data?
Yeah, that comes up, right? I mean, maybe I'll show the code later. That will be better, right? Majority of my models, the testing was in the range of, although I tried from all the way from 15 to 35%, I did not see much of a difference from 20-25% to 35%, right? I mean, even if I increase it, the accuracy and everything is fairly, it doesn't change, right? Putting in other words. But what you see here, right, in the center is the problem with this model, the linear regression model, which is that, this is obviously standardized data, right? With mean of 0 and variance of 1, right? The challenge is that the actual value you see it is 0, right? Which means that it is around 5.8, right? But the predicted values can range all the way from average, or sorry, the poor category to the premium category, right? It's showing the full range. So basically, it essentially means that it's not able to do a fair job, right, in predicting these values. And the same can be correlated with other wine values as well, right? Even the 3 to 9 wine quality spread is what essentially you have spread here, right? In the actual values.
Okay.
One question, Kiran.
Yeah.
This is linear regression problem or regression problem or classification problem?
Yeah, good question, right? Now, linear regression is typically, again, any algorithm can be used for classification or regression, but linear regression is typically used in not in the classification, right? It's used in the regression problem because, you're trying to find that linear curve that fits the input and the output variable, right? So you want to fit it into a straight line and see with the known set of input values, what is the output value? So it's actually for value estimation, right? If you look at it, like in a sales prediction or something of that sort. Okay. So it is not really, it can't really probabilistically tell whether based on certain inputs, whether it's classified good or bad, right? Good or bad way, or the loan is approved or not, right? That sort of problems, it is not within the realm of the linear regression problem.
So here output is quality. Here output is quality.
Yeah, output is quality, but it's scaled and right. So that is why you don't see the values very different, right? Not the absolute values, but you're trying to predict the output, right, from based on the set of inputs.
Okay. Thank you.
Based on the data set that training has happened.
Kiran, can you hear me?
Yeah, good.
Yeah, Kiran, I'm very new to machine learning. Just asking you something. If you go back to that particular slide, that's this one. So here I can see you have like whole numbers -3, -2, -1 for actual values, and then predicted values. So is it not a continuous data on which you are predicting Because I learned somewhere that it should be on continuous data, continuous numbers.
Yeah. Okay. So what we do, right, whether it is linear or logistic, right, regression, we do standard scaling, right? Meaning to say that you subtract, right, each specific value, right, each x with the mean and the standard deviation, right? That way,
Right.
you will see everything ranging in this value, right? Now, it is done on a continuous data, and assuming in this case everything was ideal, right? You would have seen, and again, the same thing can be plotted in the normal, like in the normal wine quality table, ranging from 3 to 9. I could have done that as well, right? But these were done. The plots were not done, or post-processed after that to actually reflect the real life scenario. But then the -3 that you see on actual value here denotes the least value in the wine quality, right? And so on. So it is, to answer your question, yes, it is on a continuous data, and it should have fitted on the straight line, right? If everything was ideal, an ideal situation. But here we are scaling the data.
I was just thinking that like the vertical lines that I can see of the scatter plots, it should not be like vertical lines. It should be scattered in a way, and then you are plotting this predictive line. Then it makes more sense. I don't know. Maybe that's why this linear regression did not work for you.
No, there are two things, right? Ideally, in ideal world, the wine quality data should have been, I should have gotten, let's say 6.5, 7.5, maybe. Yeah. So I did not have it, right? My the wine data that I got was actually not float, right? It was integer data, right?
Yeah, that's the thing.
So that is why you will see that
should be flawed
between each data point.
Yeah, have it been floating values, then I would say it would have been making more sense here.
I agree. So, or in different words, all these dots in a, assuming that, let's say the from 3 to 9, right? It is data spread like 3.1, 3.2, let's say 4, then 4.4, whatever. Then in that case, you will have seen the spread around this line, right? Now you see the clustering around these data points, because the data is such that you have that integer values, right, in wine quality.
Right.
Now, if it was if it was really continuous, yes, the spread would have been spread between the two values that you see in the window, right? But then again, even in this case, ideally you should have seen one dot across the whole line, right? I mean, in an idealistic situation. But here the problem is that even for 0, right, which will probably point to average wine, and in the actual life, you're seeing the full range for the predicted value, which is a problem here. If that range was smaller, then it would have probably made more sense.
Right. Okay. Thanks, Kiran. You can continue.
Your question was valid actually, because I was looking at the result and thinking why this happened, right? Then it quickly struck me that the data says that it is clustered in the integer category, right? I don't have decimals in the data.
Yes, exactly.
Yeah, but fair question.
Thank you.
Now I think we'll come to the question that Titi asked, right? Obviously, logistic regression is a better fit. If you're just trying to classify between, let's say, good or bad wine, right? Because it is meant to or designed to look at both the true or false cases, right? If you would think of it in those terms, and it's sort of classifying the output, right, and qualifying it literally into 2. If it is 2, then it is called binomial, right? Or if it is for a higher multiple class, then you call it multi-class or multinomial at times. I just picked 2 categories, right, and which was derived or used in the logistic regression, and I picked up the odds to show the exponential impact, right, that various features would make in the y, right, which is now a log of odds, right, or log of success to failure. So you see the free sulfur dioxide has obviously a positive impact, right? And this is something that we see in real life as well. because free sulfur dioxide actually protects the wine. So the odds improve if you have more free sulfur dioxide, right? While with total sulfur dioxide, what happens is, while it is intuitive to think that both are related, but total sulfur dioxide also brings in a side effect of having a sulfurous taste, right? And sulfur in a high quantity is toxic, right? I mean, that is at extremely high quantity, but it leaves a bad taste in the mouth, which is why you see the odds going down with this high increase in or high sulfur dioxide, right? Or increase in sulfur dioxide. So just capture that point, because that comes in later, and it's important from a model perspective as well, because the odds are exponentially related to the input variables as per this particular equation, right? Because although it is log, it is actually ln, because the log, I mean, it's not log to the base 10, but it's log to the base e. So that is the key, comment that I wanted to touch upon there. The assumptions, obviously, these are well known. The most important table, right, on the logistic regression is the confusion matrix, essentially allowing us to represent the true positives or false positives, false negatives, and true positives, right? So I also captured a confusion matrix from one of my results. There you see that, what is predicted as bad, right? I mean, and actually bad. I mean, that alignment is happening at around 487 wines, but a good wine was predicted as bad in 222 cases, right? Which is actually not a great scenario to be in. And then likewise for the wine which is predicted good, you see the actual good was probably 1218, right? Or 1218 cases, and 347 wines were predicted good, but then they are actually bad, right? And with this data set, you basically come at and compute a lot of metrics, right? Then we will talk about later, called precision and sensitivity and whole lot more parameters, which then becomes significant, right, at a later stage. So I hope everyone is clear, right, with this 3-4 metrics that we are talking about here. One talks about, the actual values obviously are important, because those are the actual positives or negatives, and the predicted variables are compared as positive or negative based on how they fall versus the actual values, right? And this is essentially treating this table as a 2-class or binary classification problem, basically good or bad, right? Or selected or not, or and stuff like that. Any questions or comments? Okay. Yeah, this is essentially on the data set, right? I mean, the rest of the parameters that I mentioned here are derived parameters, whether it is accuracy, precision, or recall, and all that, right? And this is the output that you get here, which is at an accuracy of 0.75, is the output of the confusion matrix, which is a certain function that you can use in scikit-learn, right? And the FN scores again are an outcome, and you pass on the predicted test variables to the function, right? And you get this. So the interesting thing, obviously, which is no surprise, is that FN score is higher for good wines and lower for bad wines. That's because there are more good wines, right, than bad wines. So that is a rationale why we're getting a higher FN score. But yeah, we need to see how these parameters changes when we play around with the test ratios or the algorithms, etc. Right? So that is these are interesting metrics that you should look at. Yeah, so ROC curve is sort of a complex curve, and it is, I think, used very well used in analyzing these algorithms, right? Effectiveness of these algorithms. And the red line that you see is the non-ideal lane, which is that true positivity rate increases with the false positivity rate. You would see that it is ideal to have the higher TPR at a low FPR, right? So which is the case here, right? And area under the curve is nothing but the area under the blue curve. Ideally, it could be as high as 1, but 0.8 upwards is considered to be reasonably good. Again, this all also depends on the context, whether you're trying to predict, you know, a very fatal illness like cancer versus something like a wine classification, right? Where you have a higher degree of probably error, right? So it all depends on the use case. But for my use case, I thought this was fairly okay, right? And we keep talking about all these assumptions earlier, but the easiest way to actually test whether these assumptions hold good, right? Again, this is only one of the means. There are other means to compare the other metrics, right? Like autocorrelation and so on. But for multicollinearity, this was supposedly one of the most popular metrics, right? To actually compare. And whether the efficacy of a IV, right, is relevant for your data set and your data, the machine learning model, right? And the density had a very high VAF, and hence I decided to drop it. Likewise, some other use cases I've seen even VAF greater than 5, right? They drop those variables as well. And obviously, after dropping the parameter, you test whether you know how it has impacted the model, right? So in my case, I did some of these testing, right, and I found that this did not have much of an impact, and accuracy continued to be around 75%. And I also dabbled upon one more algorithm, SVM, although that's not been covered yet. But then it is a couple of functions that we need to use, right, and to see whether the same data can be fed and you know how to do, would it change, right? And being told that random forest could give a much better potentially accuracy and FN score, but that needs to be seen, right? I have not yet done it. And KNN also was tried upon, but then the KNN probably is not as effective as logistic regression for binomial classifications in this particular data set, right? SVM did have an impact. It did make a dent. And obviously, the logistic regression may not be, you know, it's a good pointer that logistic regression may not be the best, right, of all the algorithms that are out there, but it's also a function of time, right? How many ML models that you actually want to dabble up. Because I was listening into one of the group discussions, right, with a bunch of data scientists from Google and Facebook, and what they seem to think, right, obviously their problems are order of magnitude higher. What they seem to think is that you typically tend to dabble upon only 2 or 3 ML models for a specific data set, because you need to, you have so many things, right? You're moving parts in a specific project for you to actually spend time trying all these algorithms, right? And classifiers. Okay, moving on. This is the multinomial logistic regression, right? With classification type of 3. And just so that you understand, the 0, 1, 2 maps onto average, poor, and premium wines. Please note they are not in the increasing order of the wine quality, but you know, 0 represents average, 1 represents poor, and 2 represents premium, right? And average, when you look at it, they are primarily the quality 5 and 6. So you throw any kind of wine at the model. If the wine has attributes of average wine, it seems to predict with FN score of 0.88, right, which is fairly good. But that doesn't hold good for other wines, where these are, by the way, the numbers that you see here are actually the test data points, right? And where do they fall, right? For instance, the 1219 that you see on the top left-hand corner, what that means is that the actual wine category for these 1219 wines was average, right? And the predicted output was also average. And if you go along the same row, you will find that although the average wine output was, I mean, that continued to be same, but 38 wines were predicted as premium wines, right, by the classifier. But the good part is it did not go to a wine category of the poor category, right? So average wine wasn't predicted as a poor wine, but some of them got predicted as premium wines, right? Now, this also fundamentally can be connected back to our earlier, the binomial regression, which had a better precision, right? When it comes, and F1 score when it comes to premium or the good wines, right? But not a similar score for bad wines. So the dataset needs to be improved if you were to classify the bad wines correctly. So that is definitely something that needs to be improved. And this is an extension of the study, but this may not be, I would say, ideal for this dataset, because you have 7 different types of wine ranging from 3 to 6. And if we actually classify them, then you're actually doing a prediction, right? Or you're trying to do a exponential model and then asking it to classify it for as many categories of wine that exist. So it is really, in that sense, not a classification. So I'm testing the limits that way from a classification sense, which is why the accuracy drops big time, right? And sort of you can see that when we went from 2 to 3, the logistic regression accuracy improved, but beyond that it dropped, right? I mean, and this also aligns with the histogram that you saw in the beginning, right? On how the data set is spread. So I think next task for me is to probably improve the premium and poor wine data sets and to the same algorithm, and then part of it, to be given to the training data set, and classified as training data set and given to the ML model, and then test it out and see if that makes a difference, right? This is something that we pretty much covered. Just one caveat I wanted to highlight, since there was some confusion in the group, right? I was looking at it. We use this fit and transform, sometimes standardized also synonymously, but the real fit, right, only applies to the training data set, which is to say that the information on the variance or standard deviation and mean is stored in the ML model only from the training data. This connects back to, I think, one of the things that Tithi mentioned, right, in one of the chats. We should not use that information from the test data, right? If the variance, mean, etc. of the test data, or if that leakage happens from the test data, then there's no purpose of actually doing it, right? There's no reason for classifying data into training and test. So, and this is the context, right? I mean, the scaling happens for both. That's why you see the distribution between pretty much from -1 to 0, right? For both the test and training data, but the input to the ML model goes only, via the fit, right? And that is applied only for training. I hope, I covered most of it. So do let me know if there is anything, if there are any questions or.
Yes, Kiran, so you have fit your, after splitting, you have done standardization, right? After
Yeah,
splitting,
correct. That's right. Yeah.
yeah, and you have you have used fit transform for training data and only transform for test data. Am I right?
Yeah.
Okay. Yes, solved my query. Thank you.
Yeah, and then it's important to keep it that way, because if fit, actually, by the way, that steps can be changed in the sense that I've seen both kinds of flows, which is to do fit and fit transform together, sometimes, and fit and transform, right? In this context, yes, I've used fit and then passed on that to the model, and used transform specifically to training, and then same for test separately, so that the test gets from a mean and standard deviation standpoint, the one in the training is being used for scaling both, and the model only gets trained using the training data, right? As in the variance and the mean of training is passed on to the model. The same of test is not passed on to the model for obvious reasons. But then, yeah, I mean, the flow, the fit and transform, it can be, I mean, I've seen multiple use models, right? I mean, and then there are multiple rationales apparently why people use it.
Okay.
Any other questions, guys?
No questions from me.
No. Probably if you can just quickly run through the code, that will help.
Yeah, let me do that. Just give me a sec.
You have done this in Collab or notebook?
Yeah, I've done it.
Okay. Actually, I'm not getting how to install files in Jupyter Notebook.
Sorry, I didn't get it. What do you mean files? I mean, you can there is an upload option, right?
No, actually,
You're talking about
installing
data
of,
files, or you're talking about something else?
no, installation of libraries.
Oh, okay.
That PIP is not working for Anaconda.
Yeah. No, I face some issues with the
But that issue is
Anaconda,
not,
right?
yeah, but that issue is not for collab files. That's why I'm also doing it in collab, but it's not possible for, not getting possible for that Anaconda, Jupyter Notebook actually.
Yeah. So we are, I guess, on 15 minutes past the timeline, right? So let me quickly run through and wrap it up, right? These are the EDA I will not get into. I hope that's the understanding, right? And everyone knows it in and out. I can probably check with Jagat if there are Python related questions, right? But I did quite a bit of EDA. Found out some lot of fancy graphs and all that, but then yeah, I mean, net too much of data, very other than some broad strokes, very difficult to make out, right? Yeah, but then this is something that you should look in case if you. Oh, sorry, I think it's not probably getting shared.
Yeah,
Right?
we are not able to see the screen.
Oh, okay, sorry. I was under the impression that it is shared. 1 second.